Right, okay, good. So, so the third part of the module will be about multi-user communication, and this is also fundamentals in all modern communication systems, simply because you're not the only one in a network, right? You may actually have a transmitter, may have to deliver a message to a certain users, but also at the same time has to actually transmit information to other users, right? Or you can have multiple transmitters and multiple receivers active at the same time. And so this leads a lot of to a lot of other issues, and in particular the problem of interference, which is really critical in wireless. Right, so you're going to see applications everywhere in wireless, from 4G, 5G, and beyond. You have other standards, obviously, in communications, terrestrial and satellites, where all those techniques can be used, or will be used, or are actually currently used. And it's a module that is very useful, very valuable if you want to do a PhD in wireless communications, wireless signal processing in general, or if you want to go to industry afterwards, whether you go to research centers or any R&D branch of manufacturers or operators or so on. Right, so the skills you will develop is some mathematical modeling and analysis of wireless communication systems. Right, we'll start with relatively simple things, and then we go into more complicated stuff. And the math that we use there is essentially based on two things. It relates to probability. We're going to use probability, and we're going to use linear algebra. Right, so those are the really two essential mathematical tools that we're going to use. Sami, I will answer your question just in a minute. This will come. The other thing we're going to look at is the design of wireless communication, transmitter, receiver, multiple transmit antennas, multiple receive antennas. And the last thing is really a basic system design and performance evaluations. And this you're going to play with extensively. You're going to look at this extensively in the coursework. Right, so so those are the three parts of the module. So the basics of wireless, part one, we're going to look at what is a wireless channel, what is the problem of fading and diversity, and what is the capacity of wireless channels. And so you will see the notion of fading comes with the fact that you have fluctuation of the wireless channels. This is a major difference with any other types of systems like wired channels. And you need diversity techniques to do that. And we look at lots of different diversity techniques to do that, to try to mitigate this problem. And we look at the capacity of wireless channels. What is the fundamental limits when you transmit information over wireless channels? Then we move to part two on MIMO systems. We look at basics of MIMO. We're going to look at the MIMO channels. We're going to look at the capacity of MIMO channels, how to achieve the capacity of MIMO channels, transmission and reception strategies, how can we actually pre-code and combine information. And then we're going to look at the case where actually we may not know the channels perfectly at the transmitter or the receiver, and we need to rely on some form of quantized pre-coding. This is what you have in modern systems, and so you will see what that means. And then we're going to look at multi-user communications. And so here we're going to have multiple transmitters or multiple receivers. For instance, you can have one transmitter with multiple receivers. You can have multiple transmitters and one receiver, or you could have multiple transmitters and multiple receivers. And so what we're going to look at there is the capacity of multi-user channels. So what is the fundamental limits when you have multi-user communication? And we're going to look at this when we have single antenna nodes at the transmitters and the receiver, and when we have multi-antenna nodes. And this is really the fundamental building blocks of modern communication systems in and we're going to do this for low-dimensional MIMO systems, so multi-user communication with small MIMO systems, all the way to the massive MIMO, where you have a very large number of antennas. And the last bit here will be about multi-user, multi-cell communications. So this is really representative of a cellular network where you have many transmitters, many receivers, they interfere with each other. Right, so the course material will be on Blackboard. I will finish this by this week. So I send you already all those slides. So the lecture materials actually I send you by email, but this will be put on Blackboard very soon, along with the information about coursework and some problem sheets. So the prerequisite for this module is a third-year course on communication systems, where you look at some aspects, basics of communication theory, and some aspects of wireless, like the notion of delay spread, angle spread, these kind of things. Frequency selectivity, frequency flat is something we actually will not look into any details, but at the very beginning I will briefly mention that. This module does not have any exam, so this is a change compared to, I would say, maybe now 3 years ago, where we used to have one coursework and an exam at the end. Here there is no exams, but it's based on 3 coursework. And the courseworks are based on, divided as follows: 20% for coursework 1, 30 for coursework 2, and 50 for coursework 3. And you already have the deadline here for the 3 different courseworks. The first one will be 7th of February, second one 28th of February, and the third one 23rd of March. So there is no oral for coursework 1 and 2, so you just submit a document, a report on Blackboard. But there will be an oral for coursework 3 that will be scheduled on 25th or 26th of March 2021. So this is an oral that will be to try to, where you're going to have to submit a report first, but also you're going to have 15 minutes discussions with the GTAs, where we're going to ask you extra questions and try to see whether you really understand what you have written in your reports. Right, so we have lab sessions as well. So we have the lectures. We're going to have so today we have 2 hours, but we have next week. You're going to see on the timetable we have actually 4 hours next week. I think it's 2 hours on a Monday, and I think the 2 hours on Thursday, and then on average we have usually 2 hours per week. But there are 2 weeks where we're going to have 4 hours, and the reason for this is to give you a bit more time to cover at the end for you to finish the coursework 3, so that we make sure that we finish the material a bit ahead of time, so around maybe week 8, so that you have a bit more time to digest all this and go into coursework 3. So you have the lab sessions as well. You have 7 sessions of labs that are scheduled in week 3 to 9. So it starts from not next week, but the week after. And this will be done with the GTA. So we have Longfei and Yang, who are 2 PhD students in the lab. And Longfei is on the call, right? So you can say hello, Longfei, if you like.
Hello, I'm Longfei. I'm a PhD student in Bruno's group. So we will start the lab session from 24th of January.
Right.
And you can check on the timetable.
Right, very good. So there will be problem sheets also on Blackboard. Those problem sheets will be used during the lab sessions. Right, so one more thing. So the coursework, I'm really relying on MATLAB quite a bit. There are some questions that are more theoretical, so you don't need MATLAB. But there are questions that actually requires MATLAB. And the level of difficulty is increasing. Coursework 1 is relatively easy, right? No major difficulty there. Coursework 2 is relatively easy as well, but a little bit more complicated. Coursework 3 is much more And coursework 3 is also much more interesting. So coursework 3, what you're going to do is essentially you're going to really simulate the fundamental building blocks of a 4G and 5G system. So you're going to simulate a multi-cell, multi-user, multi-antenna communications. So we're going to have to really implement what we do in the modules: multi-antenna processing, scheduling, precoding, quantized precoding, multi-user communications, and you're going to have questions on the massive MIMO as well, where you're going to have a large number of antennas and you're going to serve many users at the same time. Right, so you will see really what it means to run some simulation. Those simulations, coursework 3 will be also a bit more demanding than coursework 1 and 2. Past feedback on this module has been always excellent. So really students love it to have those courseworks. They really learn a lot. Change in this year compared to last year, you will see once I put the coursework online, I'm planning to have some more, I would say, one more theoretical questions and some more simulations on coursework 3 where you really go all the way to massive MIMO. And I'm planning to have some of those questions as bonus questions, so you can get extra marks if you really answer those questions well. Right. Right. So maybe to answer Sami's questions. So advanced communication theory is given by Professor Manikas. It's actually mandatory modules for MSc students. It's not mandatory for MN students. The advanced communication theory, the emphasis is a bit different from what you will see in this module. The emphasis is really started more from all the CDMA approach and goes into more array processing. And the array processing is really what Professor Manikas works on, which are those, what does he call this? Differential geometry, which is discussed quite a bit there. What we cover here is not treated in an array processing perspective. It's more closer to, I would say, really MIMO communication theory, as it's used in 4G, 5G in research, I would say, in the past 10, 15 years, I would say. Right, so the two modules are complementary, but the way it's presented and the emphasis are quite different, and the skills you develop are actually also quite different. So if you look at the whole coursework tree that you're going to do here, it's really something that is quite different from what you do in Professor Manikas' module. Right. Maybe Longfei, you can maybe say a word about this also, because you have taken Professor Manikas' modules during your MSc. Maybe you can say a word if you like.
Yeah, actually the emphasis different. In Manikas, the coursework is actually focused on the array processing.
Yeah.
And in Bruno's lecture, it focuses more on the 4G or 5G application and the system level simulations.
Right.
Is that correct?
I have not taken Professor Manikas' module, but I just know the content. Right, so you will see here the modules really also, if you take the information theory course, you will see connections with these modules quite a bit. So Chongling is given information theory, and it's mainly focused on point-to-point systems. At the end, it covers a little bit of multi-user scenarios, where you have what is called broadcast channels and multiple access channels. This is something we're going to play with quite extensively in the part 3 of the module. And this is really, really important when you go to 4G and 5G systems. Right. Any other question at this stage? Lab sessions are not marked, no. The lab sessions, essentially, when I say lab, you know, it's a very broad term. Essentially, it means that you can call this class, you can call this lab. It's just that is a bit more interactive than the class, in the sense that you will play with MATLAB as well. And so you're going to have sessions where actually Longfei and Yang will actually go over some problems to try to understand some problems. You're going to have part of the sessions where it's going to be really about simulating and playing with MATLAB and implementing some of those communication strategies. Okay. Good. So yeah, feel free to send me any other message or other questions. Right. Reference books. There are two books that you can look at. There is the David Say's books, the first one, which is a very good book on wireless communications, covering the fundamentals. And then you have my book on MIMO wireless networks. You can find those two books in the library, and you can find it online. You have access to them. The difference between the two is, I would say, the second one is more advanced. It really starts from MIMO, essentially. From the very beginning, chapter 1 is really about MIMO processing. This is the second edition of the book, so this is the one that came out in 2013. There is a first edition that came out in 2007, which is about really point-to-point system, single user. Here it's really about the entire network design with MIMO. So really you're looking at multi-user, multi-cell systems. Right, so this is actually a quite comprehensive book on MIMO. We will not cover all this, obviously. This book has probably close to 700 pages. So we will definitely not cover this. I will mention which section we'll cover into more details. But feel free to look at this. I think it would be very helpful to you, especially if you want to specialize in wireless and you want to do a PhD later on in that area. Right. Good. So let's start then. So with a brief introduction, so things actually you already probably know. So wireless is communication has been there for 100 years, more than 100 years, right? It really started with Marconi in 1896, but it really picked up in the 80s with the first generation of mobile communication systems, and nowadays we are actually in the 5th generation, right? So you can see that roughly every 10 years you have a new generation of mobile systems, and that means actually every 10 years you have quite different technologies that actually is used to design those systems. And why we need this is because also we see an exponential growth in mobile data. And we have a massive spectrum deficit. We have more and more wireless applications. That means actually the spectrum is getting really crowded progressively. And so what we need to do is to find really efficient communication strategies that enables to do as much as possible with a limited spectrum in order to cope with this exponential mobile data growth. Right. So the course is really about looking at fundamental communication theoretic techniques for wireless. And so the application of what you're going to learn here is actually not limited to cellular systems. You will find a lot of application in Wi-Fi, satellites, and other systems. You will find also application of some of those techniques to other communication systems. You can even have application in the wired systems. So for instance, when we're going to look at multi-user, multi-antenna communication, or even point-to-point multi-antenna communication, we're going to look at this with application in wireless, because wireless is quite difficult because of the wireless channel. But the technique themselves can be used in wired systems. But it's just a little bit easier there because the channels does not change over time. So in wired system, everything is quite stable. Wireless, everything changes very quickly. But some of those applications, some of those techniques actually can be used well beyond wireless. Right. So what are the challenges nowadays in wireless comms? Well, you have many challenges at different level. At the network level, at the radio channels, radio challenges level, increasing data rates, the limited spectrum, I mentioned this, the reliability and coverage of the systems, coping with mobility, increasing mobility, not only pedestrian, but all the way to several hundreds of kilometers per hour. Energy efficiency is increasing important as well, right? You want to deliver as many bits as possible per unit of energy. Latency, right? This is something is increasingly important in 5G systems. You want to decrease the latency in the network as much as possible to enable driverless cars and things like this. And the fact that you have really an explosion in the number of devices. So all the access point, transmitters, receiver, they have to cope with many different devices. You don't have only one device on the channels, but you can have many of them. You can have, so this is really about, you know, the design of the communication strategies, but you have also a lot of challenges for people doing RF design and chip design, right? So all those techniques, all those communication and signal processing techniques that you actually come up here will ultimately have to be implemented on chips. And so you have a lot of issues there that needs to be tackled in terms of performance, complexity, size, power, cost of all those chips. Increasingly, when you go to higher frequencies, so now in 5G, you go into millimeter wave, so you need to actually also design the RF, so the radio frequency chains to cope with those high frequencies. How multiple antennas is very important. How you pack multiple antennas into a device is actually a quite complicated operation as well. The more you put antennas close to each other, the more actually you have mutual coupling among them, and you may want to avoid that. And then multi-radio integration and coexistence is a device nowadays. You don't only have, let's say, a 4G or 5G phone, but you have lots of other types of radio communication that actually implemented on the same. So actually, those people doing, you know, chip design, they have to integrate different radio systems into the same chip. Right. Then you have aspect of spectrum and regulation. So the spectrum is limited and is controlled worldwide by organization like ITU, so the International Telecommunication Union, who actually kind of split the spectrum into frequency bands, and then those different frequency bands are allocated to different applications. And so you need there's a lot of work done on regulation and spectrum allocation by ITU, but by also different you know, organization that you have in the different geographical zone of the world. And the reason why you do that is because you want to make sure that there is some form of interoperability, and that when you move from one country to another country, your system will still work, essentially, ultimately. And if you don't do that, you end up having a lot of interference between the communication systems and, I don't know, a system that is used for astronomy, for instance. If they're both used on the same band, you can imagine would have disastrous performance. Now you have standard as well, right? And standard are really what also helped, and is one of the reasons why actually wireless became so dominant, is because of is thanks to the help of those standards that really make sure that those systems can interact with each other. So if I have a phone from let's say from Samsung, and you have the network is designed by Huawei, you want to make sure that actually those two understand each other. If there is no standard, it means actually there is no common language that needs to be implemented onto the phone and onto the network. And that means actually a phone of Samsung will not be able to communicate with the network of Huawei. Now, thanks to those standards that define the fundamental technology that needs to be implemented in all devices worldwide, you can actually make sure that whatever, you know, brands you have and whatever country you go, essentially your phone will work, right? So this is very important for the adoptions of those technologies worldwide. Right, so the way it works is that in those standards, and you may have, 4G, 5G are just different standards. They are run by what is called 3GPP, and all those companies involved in those standards, and you have a very large number of them, and all the major ones. What they want to do is to have the technologies essentially adopted in that standard, because that means actually it leads to a lot of potential intellectual property revenues as well. Right, so whenever you actually have a new technology and that is adopted in the standard, and this technology is patented and is used by billions of devices worldwide, is actually it can be a big revenue for a company, right? So, for instance, in 3G, Qualcomm in US, I think, on each phone each phone sold worldwide, I think Qualcomm was receiving $7 per device, right? Just because of their intellectual property, right? So you can imagine other companies like I don't know, Samsung, who's selling billions of devices. If they have to pay $7 per phone to Qualcomm because of intellectual property revenue, it's a big hit, right? So this is why all those companies invest so dramatically in research and development, is because it produces a huge amount of intellectual property that plays a big role in the technology development and the standard development. Right, so for me, for instance, before joining Imperial, I worked for Samsung Electronics for 5 years. So I designed 4G. So actually, I designed all the physical layer of 4G, including all the MIMO processing. And so, for instance, the phone you're using now, you're using 15 of my patents that actually are adopted as essential patent in 4G. So all devices worldwide are using 15 of my patents. Unfortunately, I'm not rich because all those intellectual properties belong to Samsung. But this is just to show you how actually impactful the work you can do in wireless can be. You can do a PhD in communication, go to a companies, and if your techniques actually from your PhD is adopted later on in a standard, the impact can be quite significant. So this is what I did between my PhD and my work in Samsung. So all the work we do in the lab, for instance, in my lab upstairs where we have 15 PhD students, is actually to work on really fundamental techniques for future communication systems with potential applications in nowadays in 6G, right? Obviously, we never know what actually this will be used ultimately, but this is what we're doing. Right, so standards, you have IEEE, you have 3GPP, those are really the big ones. Right, so for instance, Wi-Fi comes from IEEE. This is the Wi-Fi, and you have many others. 3GPP, you have all those 4G, 5G, and so on. Good, so this is just a general introduction. So what you have in 5G currently, if you compare to 4G, so this is LTE Advanced, this is 4G. This is beyond 4G, this is, as you can say, 5G. If I, very naively, you have a density of nodes actually increasing, and you have many more antennas, right? So this is something that really happens. So you go from here, typically you may have, I don't know, 8 antennas at the transmitter and the receiver at the base station. Here you start having maybe 100 of them. So you go into a massive MIMO scenario. Here you may have lots of different nodes. You have macro cells that cover quite large areas. Then you have those little cells, picocells, femtocells that cover small areas. And they may potentially all interfere with each other. So you need to coordinate the interference across this entire network. When you go to higher 5G, you have the density of those nodes increase. So all the users actually closer to the access points, and that also increase the performance, right? So this is a very naive approach. We'll go into this much more detail later on. Right, 5G is not only about more antennas and more cells, you have a higher frequency band as well. And the reason for this is because in the sub 6 gigahertz band, which are really usually the bands that are the most favorable for wireless communication, well, it's getting really crowded. Right, so this is an example, we don't see it very well, but this is an example of the frequency allocation that you have in the whole RF spectrum. And so you have at the low frequency is here at the beginning here. The higher frequencies actually is here. So you have your AM radio, TV broadcast at really at low frequencies at a few megahertz level, and then as you increase the frequencies, you get the 3G, 2G, 3G, 4G is maybe around the 2 gigahertz here. Frequency band, the Wi-Fi is maybe 5.18 gigahertz, something like this. So you have the sub 6 gigahertz band here, and you see actually you have many of them. If you zoom into this, you have a lot of different applications, different systems, not only for communication as you know them, but you have radio astronomy and many other things. And so if you really want to increase further the data rate, the problem is actually you don't have the bandwidth available. So either you keep the same bandwidth and you need to increase the efficiency, the spectral efficiency of the system. And this is where the MIMO comes in, is the MIMO really boosts the spectral efficiency significantly because it uses the same spectrum, but it uses the spatial domain in a very efficient manner. The other way is to try to find higher frequency band, and one way to do that is to go to much higher frequency spectrum. And so this is what you have here, for instance, in the 28 gigahertz and higher, where the wavelength is much smaller, but the propagation loss can be also quite significant. And so in 5G, you have typically an operation around the 6 gigahertz, below 6 gigahertz, that will enable you to have very good performance over relatively large coverage. And then you have the much higher frequency band, the 28, 38, 60, and so on, which leads to severe propagation loss, and so for which the coverage or the cell size would have to be essentially smaller. Right, so, but you have much larger bandwidth, and this much larger bandwidth enables you to actually boost the data rate quite significantly. Right, so this is just to give you a general overview of what's going on, and so you understand a little bit the context. Right, so future wireless networks, so all the things actually we're going to be looking at. You can use this in many different applications, and here are some of them. Right, so you have obviously what we all talk about is the 5G and beyond, but those 5G and beyond could have, application in, for instance, smart homes, smart cities, IoT, autonomous cars, right, that will be coming in the futures, body and area networks. So when you have actually a network of sensors that actually is on your body or inside your body, and they have to communicate, all those nodes have to communicate with each other. It's not limited to terrestrial systems. You can have satellite systems, right? For instance, Longfei is working on future, communication theoretic techniques for future satellite systems and integration of satellite and terrestrial systems. You can have drones, right, and UAVs. That's also popular. So you have a flock of drones flying around. How can you design communication for all those drones? You can have molecular communication. So this is using wireless communication theory, but to apply this at the molecular level. So inside your body, how you can use molecules to actually convey information among themselves. And so the molecules inside the body, there is already some form of communication that is ongoing through biology. You can model this using communication theoretic tools, and you can also think about how molecules can actually convey information from one to another. So this is also an area that actually is looked at. Application of communication in health, biomedicine, neuroscience. How can you model the brain, for instance, as a communication network? And so all those neurons are firing and transmitting information to each other. You can view this actually as a communication network and use tools from communication theory to analyze this. You have also other things that are going on. Energy harvesting, power transfer, right? So you may want to use wireless in the future, not only for communication, but also for power transfer. So then you use the radio waves for the dual purpose of communicating with device, but also for charging them. This can be very helpful if you have a really large number of them, and because you have trillions of devices, you cannot change the battery or charge those devices constantly. So you want to make them completely autonomous through energy harvesting or wireless power transfer. Other activities that are ongoing in the research, right? So lots of those activities are things actually we're doing in the lab as well, in my research lab, but you have integrated sensing and communication, right? So how can you use wireless to do sensing and at the same time to do communication? Sensing could be radar, could be localization, could be other things. So you can view your whole wireless network in the future as a way to actually have giant sensors that would sense, you know, what people do, what happens around you, but also for communication. So you have the power transfer, you can have sensing, you can have communication. So those future wireless networks may be much more than just communication per se. Lots of work on new materials for future communication, new surfaces. How can you implement those, you know, those many antennas, for instance, instead of having those base stations, those towers that you see with many antennas, how can you integrate them into buildings, for instance? And so you're going to have giant surfaces. So when you build your house with bricks, essentially those bricks will already be fused with some kind of antennas, if you like, so that the giant wall, the whole wall can act as a form of intelligent surface that would be able to control the wireless channels and the propagation. And lots of new algorithms, optimization, learning, machine learning techniques also that are used for communication, for wireless, in order to improve the design of the network. Right, so that was an introduction, essentially to the world of wireless in very, very briefly. And now we're going to start looking at some more technical stuff, right? Starting with the basics of wireless, the part one. Any questions so far? No questions? Okay. Good. So let's look at this. So here I will look at 4 different things. The first one will be about trying to clarify a little bit the system model that we're going to be looking at. And so this is starting from the discrete time representation. This is something that you have seen already in your previous communication course. But I will go over it very, very briefly to try to show you where the system models that we use, where does it come from, essentially, very briefly. Then we're going to look at the wireless channels. So per se, we're going to try to characterize a little bit the wireless channels, what it is made of, look at fading and diversity, and then the capacity of those channels. So this is not only for today, probably this is going to be also for next week. Right, so some of the things I'm talking about is actually in chapter 1 of this this book. Some aspect also actually in chapter 5 of the David Say's book. Right, so feel free to have a look at those sections if you want to have more details about the content of those lecture notes. Right, so this is the discrete time representation. So here actually what I want to do is to try to show you what is the system model that we're going to be using. And then just to show you already ahead, I will jump a little bit just to show you what we're going to play with. What we're going to play with is actually a relatively simple equation. It looks like this. It looks like this. So essentially you have a yk, which is a received signal at, let's imagine you have a transmitter with one antenna, and you have a receiver with one antenna. And at your receiver, you have a y of k. At the transmitter, you transmit a c of k, right, at time k, essentially, that's what it means. So you have an information that you transmitted at time k. You have an observation at the receiver at time k. And this observation, those two, the receiver and the transmit signal, actually relate to each other through this relationship. H of k will be the wireless channel, and n of k here at time k will be actually the noise that is here generated at the receiver. Could be maybe a terminal noise, could be also include some form of interference later on. But for the time being, you can just assume this is some kind of noise, Gaussian noise. Right, so this is actually the system model we're going to play with in the first part. And then in the second part, we're going to expand this when we have MIMO. So we're going to start having vectors here, and vectors there, and vectors there, or matrices there, as well. And here the H can be vectors or matrices. So we're going to start playing with higher dimensional quantities. Right. So this is actually the system model we're gonna look at. Now, to get to this, for you to understand where this comes from, we have this discrete time representation, so that you understand a little bit what are the assumptions to get to that relatively simple model, system model that actually I just mentioned. Right. So what is the channels that? What are we talking about when we say channel? What is this? Well, they're actually, depending on who you talk to, you may have a slightly different definition or interpretation. If you take an information theory course, the channels may be actually represented in form of some form of probability density function, or condition probability density function, or mass function, or something like this. Here, the channels in these modules will be a little bit closer to what you could say in what you have in linear systems. You will view this as simply an impulse response. Right? So you can first view this as the impulse response of a communication system that is modeled as a linear system between one transmitter and one receiver, or you could have potentially between more than one transmitter and more than one receiver, or more than one antenna and more than one transmitter antenna and more than one receiver antenna. But you can view this as an impulse response, right? People can call also channels in the frequency domain. So that's your frequency domain channels would be actually a Fourier transform of the impulse response, essentially. Right, so for the time being here, let's assume we have a SISO transmission. So SISO means single input, single output. So I have really one transmit antenna, one receive antenna. And what I'm having here is I want to transmit a series of complex symbols, CL, right? So I have a series here of symbols that I transmit. Let's say C0, C-1, C-2, C1, C2. And those actually are transmitted at a certain symbol rate, right? Every TS, and TS is your symbol, your symbol rate. So every TS you transmit a new symbol, essentially. That's what it says, right? Now those CL here, what are there? They could be, for instance, QPSK symbols or 16 quam symbols or whatever, symbols coming from, let's say, a constellation. Right. Now I'm writing my transmit signals. It's not transmitted yet, but the one in baseband I would like to transmit is essentially a train of Dirac pulse. So your delta here is a Dirac pulse. So I have a Dirac pulse here for each of those. And this Dirac pulse is multiplied by this constellation point. And I multiply here, and those constellation point here, those constellation symbols, they are taken from a constellation that I assume has a unit average energy. So for instance, if you have QPSK, you have those 4 points, right? And the constellation here has on average unit energy. So that means actually here, for instance, this point here would have, for instance, 1 over square root of 2 plus J 1 over square root of 2. And you can have something similar for all of them. On average, the energy of this constellation will be equal to 1, right? The magnitude here will be equal to 1, essentially. Right, so the ES here is a way to scale that energy of that constellation. So if I increase ES, essentially, it means actually I scale this. So I inflate the constellation, or actually deflate it, depending on the values of ES. Right? So the ES is related to your transmit power, essentially. Right? As you increase ES, you actually increase your transmit power. Right, so now I have a transmitter. Essentially, I have the sequence CT in my transmitter, right? and I have a receiver, and I will receive at the receiver an observation y of t, right, that I have here. So this is what I have at the transmitter, this is what I have at the receiver. And what I have in the middle here, right, that incorporate part of the transmitter and part of the receiver is a black box. And this black box has a certain impulse response. And this impulse response here is defined as HBT tau. Right, so what that means is that B here stands for the fact that I have a certain system bandwidth, B, that is directly inversely proportional to my symbol rate. So it is 1 over my symbol rate. And I have two dimensions here. I have the time and I have tau. So t is the time, same as here, there and there. And tau is the delay. So what that means is you can view the delay as echoes, if you like, right? So at a certain time t, right, you're going to have an impulse response that may look like collections of lots of echoes, right? But as your time increases, as you change your time, those echoes, the shape of those echoes may change because, for instance, your environment change or yourself, you move. So you may have a time varying systems. And so that impulse response will change, right? So if I draw this very briefly, I could have something like this. I have a delay and I have the time, and I can have an impulse response that will look like maybe something like this at time 0. And as it evolves over time, maybe that impulse response later on will look like this, for instance, right? The echoes, right, around this time here, around this echo here, around tau here will be different at those two different times because the channel is changing over time, right? So you can think about really this as really an impulse response of the systems. And so what that means, this delay here, this tau, it means that it's the response. So the impulse response at time t and delay tau is the response at time t of an impulse that was transmitted at time t minus 2. Right? A delay, you can imagine if I transmit an impulse from my transmitter here, and I have a receiver there, I may have an impulse, for instance, that will travel in line of sight, but I may have an echo that may bounce against a building or against a mountain, and that will arrive at the receiver with a much longer delay, right? And so this is what characterizes a little bit this tau, is this delay in the propagation, because you may have potentially multiple paths, or you can view this as a certain, essentially, filter. Okay, so what you do if you have a linear system, essentially your received signal is a convolution between your transmit signal and your impulse response, and this is what you have here. And so you can write this, generally speaking, as an integral of your impulse response and your transmit signals, and you integrate over the whole duration of that impulse response that may have a maximum duration, for instance, here of tau max. Okay, so this is really a linear system. You have an impulse response, you have a train of symbols, and you transmit this, you convolute the two. Correct. Now, what is this h of b? This h of b is actually, I was saying that actually this is a black box here. This black box contains part of the transmitter, part of the receiver, and part of the real wireless channels. And so this is expressed as the following. This black box, this impulse response, is actually itself could be viewed as a convolution of three different filters. We have the pulse shaping filter, the transmitter. We have a pulse shaping filter, the receiver, and then we have the impulse response of the true channels itself, so the electromagnetic channels. So what we have with h of b is already the channels, the impulse response of the channels, but that includes some of the filtering that you have at the transmitter side and the receiver side. Right. Now, if you have an ideal communication systems where, let's say, this h here in the middle is equal to 1 simply, and so here you have simply a convolution of the transmit filter and the receive filter, you have seen in previous communication course that according to Nyquist, you need to make sure that this concatenation or this cascade of those two filters does not create any interference between symbols, right? And the way you do that, you design those filters here, for instance, using raised cosine design, raised cosine filters that will enable you to actually have a communication systems where if h is equal to 1 here, this part here, you actually do not have interference between symbols. So what that means is that if you have this train of symbols here, and you convolute now with a raised cosine filter, you're going to end up with something that may look like this. I have the C0, C1, C minus 1, C2, C minus 2, sorry. Right? If you have some good filter that wants to avoid the interference between symbols, essentially, you're going to end up with something look like this, right? Right, and then here you're going to have actually a waveform that will be superimposed on C minus 1, on C0, C2. And so what you do at the receiver, you will actually receive this train of symbol that is being convoluted by this cascaded filter here that satisfy the Nyquist criteria based, for instance, on raised cosine filters. And when you sample at the receiver to receive your signals, you actually samples at the peak here, or peak there. And what you see that when you sample at C0, you don't experience any interference from the symbol C minus 1, the waveform here of the symbol C minus 1. And so if you sample here at time 0, you're going to have this point here, and you're going to have nothing coming here. All this other waveform here goes to 0, so you don't experience any interference from the other symbols, right? So similarly for C1 here, you're going to have something that looks like this, right? So you don't see any interference from C minus 1 and C1 because this waveform goes to 0 at this sample time. Right, so this is what the interference between this raised cosine filter does and this Nyquist criteria does. And this works really well if you have an ideal systems where actually you have here no wireless channels. Now, in general, you don't have a 1 there. You may have something that is much more complicated because you have yourself in the electromagnetic propagation, you have really echoes, and the examples I gave you before really comes into play here. If you have echoes against a wall, against a mountains, against a building, that will actually impact the shape of this H here. I won't have just a 1. I may have an echoes that really looks like in delay profiles. I may have some echoes like this, right? And some of them may be stronger than others, right, depending on the propagation conditions. So on top of having this raised cosine filter, now what may happen because of this what we call multipath propagation, you end up with something where you may have something like this. Right, this is maybe for C0, and then you have for C1, you have something like this. Right, and for C2, for C minus 1, for C2, for C1, you have something like this, right? So what that means, I'm sorry, it's always easier to do this on a board, but what that means is that essentially, if you look at this point here, now if I sample at this time, I have my symbol 0 is actually encoded into this waveform there, but actually I am corrupted by the blue one and the green one. So when I'm looking at my observation at time 0, I'm going to have the information from C0, but I'm also going to have interference from the symbol C minus 1 and C1. So this is this interference between symbols. And that comes from the fact that now this H of B here does not satisfy these raised cosine filters criteria anymore, and then I have this interference between symbols. Right? And so this is what you see here in this relationship. What I'm doing here is simply I'm taking the C of t here, and I plug this C of t into this relationship here. So I'm doing the convolution, and because you have a train or a sequence of Dirac pulse, if you convolute this with any impulse response, of the channels, essentially, you're going to have the impulse response of the channels will be replicated around each of those Dirac pulses, right? And this is what you really see here. You can view these black curves here as you'd say that's the impulse response of my channels, accounting for the transmit and receive filters. And I replicate this around each of those symbols, each of those Dirac pulses. And so this is what you see here. What I end up with is essentially still a sum here, and that sum comes over L comes from because I have a sequence of symbols there. And then instead of having a Dirac pulse, now I will have the impulse response of the channels evaluated at T minus LTS. And this is what you have here. So this quantity here is just a change of notation. This is the same as saying this is H of T, but with a delay that is given by T minus LTS. Sorry. So what that means here mathematically is just what I expressed there, is that at a certain time T, whatever time T, you see that you will not have, you will have actually a contribution from many symbols from minus infinity to plus infinity, and each of those symbols will be actually multiplied by a certain contribution of this impulse response here, right? And this, because this quantity is non-zero in general for all terms from minus infinity to plus infinity, you're going to have interference between symbols. If this quantity is actually equal to 0 for all except for 1L, for instance, then you're going to end up with just no interference between symbols. Right, so this is a very crash course, you probably have seen this many different ways. It's going quite quickly over this. But so this is your received observation at time t. Then you sample it. So you have an operation. Oops, what happened? So you have your receiver. What it does is this sampling at symbol rate. So you have your sequence of pulses, right? It goes into your transmit filter. It goes into your wireless, the wireless channels. It goes into the receive filter. So this is your transmit filter. This is the wireless channel. This is your receive filter. This is your big box I was talking about before, H of B, that includes the filtering and the transmit and the receiver. And what you get here at the receiver, you have your Y of T, and then you sample it. You sample it here at a period of the symbol rate, right? This is what you see here. So now you have actually a sampled version of your received signals at time k, and your time k is just a multiplier, an integer multiplier of your symbol duration. So at every symbol duration, you actually sample, and you get your receive observation in the discrete time at every time k. That is just a multiple of this symbol duration. Right, so let me give you an example. This is my sampled version of actually the expression I had just early on here, where t now is equal to this. So I sample at a multiple of the symbol duration. I can have a shift here, can take the t0 equal to 0. That's not really a major problem here. But what it means is the following. Imagine you're actually at time k, and you have so your k is equal to 0 in this expression here, but you have two taps. So you have among this here, this quantity is only for two values of L. You have this quantity here is non-zero, right? So that means actually, for instance, here I'm going to have this for L equal to 0, and my k is equal to 0. So k minus L, and L is equal to 0. I'm going to have 0. And I have for L equal to -1, for instance, L equal to -1. So I'm going to have a k equal to 0, and -1, so I'm going to have H0 at 1. And so what we have, if we have only two values of this quantity that is non-zero, all the rest are equal to 0, essentially the sum here boils down to just a sum over two values. I have the values at C0 and the values at C-1. So C0 is multiplied by essentially the impulse response of the channels, if you like, but evaluated at time 0. and delay 0. So it's the first tap of that effective impulse response after sampling. And the second one is the second tap. And so my symbol here, C-1, is actually an information that I transmitted at T symbol duration, at TS duration prior to time 0. So it's actually a symbol C-1 has been transmitted prior to symbol 0. And so what you see here is that I have an observation at time 0 that is equal to the symbol 0 that I transmit multiplied by some coefficient, but I'm also corrupted by the symbol transmitted at the previous time instant at a TS second, if you like, prior to 0, so the previous symbol instant, and this is being corrupted by this second tap, right? So if the second tap here is equal to 0, then things are fine in the sense that what you transmit at time 0, what you receive at time 0 is directly related to what you transmit at time 0. But if you have an impulse response that actually is sufficiently long, what will happen is that what you receive at time 0 is not only a function of what you transmit at time 0, it's also a function of what you transmit at previous time instance. Right? This is your interference between symbols. The C-1 interfere with the C0 that you transmit at time 0. So you have to know that, and this is very important in communication systems because you have to make sure that this creates interference between the symbols that you transmit, so you have to get rid of that. Right. So this mathematical representation is actually the same as what we had here. Here, if I'm sampling at time 0 here, and I will be corrupted by the symbol C-1 and C1 because the blue one and the green one here do not pass by 0 here. That's what it says, right? Visually, right? Right, so when does this happen? This happens really when, despite the fact that you have raised cosine filters and you satisfy the Nyquist criteria, this happens when actually this the impulse response of the electromagnetic channels, when you really ignore the effect of the transmitter and the receiver filter, when it has a certain length, essentially, and this length is not negligible compared to the symbol duration of your transmitted signal. So what that means that, very simply, that you can imagine that if I transmit a new symbol every TS, but I have some delay on my path that is much longer than TS, it means that I will have a symbol, for instance, that I transmit from here. I have a receiver. At time 0, I transmit a C0 that will travel through this, but I will also have the symbol transmitted at the previous time instance, C-1, that will arrive at the same time because it took actually a longer path, and this one was reflected along a building, for instance. So that length here relates to this delay of this impulse response, and if this delay is actually very long compared to the symbol duration, you will end up with a lot of elements here in this sum. If this delay is very small compared to the symbol duration, as you have here, then actually the strength of this component here is negligible. You can say this is equal to 0, and what you have is a direct relationship between Y at time 0 and C at time 0. So you don't have interference between symbols. Okay? So this relates to the notion of frequency selectivity. You can view this in the frequency domain. All this is something that you have seen in the third-year course on communication by Professor Manikas, and probably that was discussed again in the advanced communication theory course, right? So I will not go into all this. What we're going to assume in this module is that essentially we have a system that is such that the symbol duration is actually longer than the maximum delay in this wireless channel, such that essentially I can ignore the interference between symbols here, and I have that my receive observation at time k is equal to the observation at time ck, at the transmit signal at time ck, multiplied by my channel at time hk. Okay, so that's assumed. That's what we call narrowband or flat fading scenarios. This is a narrowband transmission. This could be, you could view this as a wideband transmission. Now, why we look at this is because you can always convert a wideband transmission using modern techniques like OFDM, or orthogonal frequency division multiplexing. You can break a wideband transmission into a lot of adjacent small band transmission. And each of those small band, you have a system model that looks like that. Right? That's the reason why we do that. So if you have, for instance, a 100 megahertz channel or bandwidth, you can split this into small chunks, and on each chunk you can transmit a new information, new symbol CK in the frequency domain. And because those chunks are actually very narrow, essentially you can do this on each of those frequency chunks. And this is what is done in 4G and 5G using what is called OFDM. Right? You may have seen this before. That may have been discussed by Professor Tanikas as well. I'm not sure about this or in the third year, but this is not something we're going to go over OFDM. If you're interested, you can look at this in the two books that discuss OFDM. Right? So this is where essentially it comes from. That's a system model that we're going to play with. So looks like simple like this. We'll see that things will get already sufficiently complicated with just this scenario. Right. Any questions here? Let's kind of diversion a little bit before we really jump more into things that are more related to this module, but it's important that you know what are the assumptions. Good. So the wireless channels, I was telling you early on that you can have reflections, right? And so for a given bandwidth, you want to have, in the scenario where we assume that essentially we assume that we have the symbol duration here will be larger, much larger than the delay we have in these wireless channels. You can view this differently in terms of coherence or bandwidth, where you can say it means the frequency domain. It means that if you have frequency selective channels, it means actually the magnitude of the channels in the frequency domain fluctuates. And if you have a large TS, it means actually the 1/TS is small, so your bandwidth is small. And so over your bandwidth, essentially you have a channel that is frequency flat. That's another way of interpret this. This is what you may have seen in year 3 course with Professor Manikas. Right? So this is what we're going to assume here, that we're going to have for our given bandwidth, we have the delay of the channel is actually reasonable, is not too large to create interference between symbols. But we're going to still have the multiple path there that will contribute and that will play a role into the shape of this h of k here. So h of k will still be coming from the contribution of multiple paths, but all those paths arrive within a certain delay tau max that is smaller than the symbol duration. Right? So why do we have those multiple paths? It's because between your transmitter and your receiver, you can have a lot of different echoes, and those echoes comes from different interactions between the electromagnetic wave and the environment. You can have a line of sight, for instance, between the transmitter and the receiver. You can have just a reflection on a flat surface, for instance, so direct reflections, specular reflections. You could have diffractions around corners, so those are different electromagnetic behavior you can encounter, and it all depends on the frequency of your system. And you can have diffusion as well, so those are all different type of things you can have. For instance, if you have a diffusion, typically happens when the wavelength of your electromagnetic wave is relatively the same order of magnitude as the granularity of your object. So for instance, if you have a wall and this wall is not a perfect mirror, but has some imperfections, and those imperfections have about the same magnitude as a diffusion, then you're going to have some interaction between the electromagnetic wave and your wall, and you're going to have you're going to have a diffused waves after interactions with the wall. If you have a perfect mirror, and that happens really when you have those imperfections that I talked about of the wall are much actually smaller than the wavelengths of the waveform of the transmitted signal, then if you like the radio waves will actually not interact with with the wall in a diffusive manner, but will just be reflected as if it's a perfect mirror, right? So this is what happens in reality. In this module, we will not go into the electromagnetism of that. Some people work on that. We will not do that. We will abstract this using a probabilistic model, essentially. That works relatively well. Now, the important thing is that you have, apart from those multipaths, you have that the wireless channels changes over time and with different time scales. So you have a long time scales and you have a short time scales. Now, the long time scales comes from what is called path loss and shadowing, and we will see the notion of path loss and shadowing in a minute, but it just means that it's something that will change over time, but relatively slowly. It's mainly a function of how far you are from the transmitter. You can imagine if you're far away from the transmitter, your wireless channels, your HK here, this quantity here, the strength of that quantity will be relatively small if you're very far away from the transmitter, right? That's quite natural. But this relates to the notion of large-scale fading, and this quantity will not change too much. If you move around, this quantity will not change too much because it's mainly a function of the distance. So if you change just 5 meters, but you're already 500 meters away from the transmitter, I mean, the path loss or that quantity will not change too much. But you have also the short time scale, which is actually the effect of those constructive and destructive interference from all those multiple paths. And those one can change very quickly. So if you just move half a wavelength, all those different multiple paths will actually interfere constructively or destructively. And this creates what is called a small scale fading. And sometimes we just call it fading very simply. And this can change at a very short time scales. So the long time scales maybe, I don't know, seconds level. The short time scales, we're talking about milliseconds level, right? So if you move by half a wavelength, a little bit, your channels may change completely at the milliseconds level, right? And this is a major problem, and this is what we're going to have to look at. Right. So what is the large scale fading, the path loss and the shadowing? So I mentioned is at the level of seconds. You could, if you don't even move, right, it could be really the level of minutes, right? Imagine you have a transmitter and receiver, the transmitter does not move, you don't move. There is no reason, if the environment around you does not move, nothing change. But you could still have some change in the environment. This is what you have in reality. You can have, for instance, just if you have the leaves of the tree that change, you could have actually some change in the environment. If you are moving very slowly at a pedestrian speed, right, you can have change in the path loss as well, but it typically range between seconds and minutes. And this quantity is very important for cell site planning and rough estimate of network performance. Cell site planning, what that means is that where are you going to locate your base stations, for instance? So you have this network here, right? This example here, right? You have a network like this, right? Imagine you have a network like this, but at the size of London. And your question is, where are you going to locate those ugly base stations that you see with all those antennas? Are you going to put it on top of some of the Imperial College building, or are you going to put it on top of the Royal Albert Hall, right? All those questions are mainly related to the path loss and the shadowing that you experience around that in that environment, right? So this is what is called cell planning. Right, so how do we model this large-scale fading? We can look at different techniques. So the first one is purely electromagnetic. So you take Maxwell equations, you have a transmitter, you have a receiver, you put buildings, you model all your buildings, and you run Maxwell equation, you solve them, and you figure out exactly what is the impulse response of the channels at a given point in space, given that you have transmitted that impulse from a given transmitter, right? And this will change whenever you change a building, you change something that moves around, or you move, this impulse response will change, and from there you can infer what is the part of the impulse response that changed more slowly, which is this passes and the shadowing. So what is the part that really primarily a function of the distance? You could have, this is very complex, this is not very practical, obviously. Very simple one, free space path loss, two-path model. I will look into this. This is really what happens if you assume that I don't have any building now. I just have a line of sight between the transmitter and the receiver. I have free space. And so the decay of the received power will be primarily a function of distance between the transmitter and the receiver. I can have ray tracing model. The ray tracing, what it does is actually try to trace rays between the transmitter and the receiver. And so if you have a transmitter and a receiver, you can plot the buildings like this. And what it does, it tries to trace all the rays that actually arrive at a certain point in space here, given that it was transmitted here. And you look at all the rays that actually have been reflected by buildings and that arrive at this point in space, right? So you can view this as a kind of simplified way of doing the Maxwell equation. Maxwell equation is really looking at the electromagnetic behavior. Here, you try to really trace rays, and it really works well when you look at those specular reflections first, and you can incorporate additional effects like diffractions and diffusion, but then things gets quite complicated. But again, same as for Maxwell equation, you require to have site-specific information. So you need to know where the transmitter is located, where is the receiver, where are the location of all the buildings, and so on in order to do that. Simplified models, power fall-off models, good for high-level analysis. We'll see this. I will show you this in a minute. And then empirical model, standard-based model is not very accurate, but they are quite useful for different designs. Some of those is really what is used a lot in 4G and 5G design. So if you go to standard meeting, they rely extensively on this kind of model. You will see when you look at coursework 3, you will use one of those very simple model. They are much more complicated model, but you will use a very simple model of that I will go over in a minute. Right, so let's go into this one, free space model and the two passes. So what is free space model? It's something that you must have seen in your first course on, if you had course on I don't know, on radio propagations or things like this. Essentially, you're looking at just free space. So if you have one source, or even electromagnetism, so if you have one source here, which is my transmitter, and I radiate, right, electromagnetic wave isotropically, so that means actually I radiate it around a sphere like this, right? And this sphere has a certain distance here. This is r, which is the distance between the transmitter and the receiver, right? So what you see here is that I transmit something with a certain power, that is PT, and what I receive at my receiver here, for instance, is a certain power, PR, right? But because I blasted energy isotropically all around that sphere, I will collect only a fraction of that energy at the receiver, right? And this is what this first equation tells you, is that your received power at a distance r from the transmitter, when you transmit it with power PT, is a function of the directivity of your transmit antenna, directivity of your receive antenna, which is essentially those two relates to the effect of the antenna at the transmitter and the receiver. If you have an antenna that actually radiates more into certain directions like this, you're going to have very little information, actually a little, not information, but energy that will be broadcasted in this area, for instance. And if you have an antenna that actually look at that direction, so you can actually have some more, you're going to collect more energy in a certain direction as well. And so that relates to your directivity of your transmit antenna and receive antenna. But the more important part is this one. You have a decay here that is in r squared, right? So as you increase the distance, essentially, you have a received power that will decrease. And this received power also decrease with the wavelength. So if you decrease the wavelength here, your received power will decrease. So if you increase the frequency, this term will actually decrease. Right. Now you can view this in dB. So you take a log of this, you're going to have your received power in dB, your transmit power in dB, plus the gain of the antennas, plus this quantity. And the minus this is called the pass loss. So minus this quantity, or 20 log of 4 pi r divided by lambda, which is this, is called the pass loss. It's called pass loss, but it doesn't mean actually it's a loss. It's not a loss because of you have something in the environment. It's just something that you can't beat. Is the physics of it. It's not a loss because you have air, for instance. No, it works. It's valid for the free space. So even if you have no air, no interaction with the molecule, the oxygen molecule, the gas in the atmosphere, and so on, you're going to experience this. So even if you go to the atmosphere and it's really the free space, you're going to have this. You're going to experience this. Right? So this is called pass loss, and it essentially decays as 1 over r squared. So the larger r, the smaller your received power. Right, so two-pass model, what is the two-pass model? It simply says that if you have a transmitter and you have a receiver that is, show this better. So let's say, imagine I have a receiver here, right? I'm here with a phone. I have a transmitter here. The two-pass model says the following. I may have a pass that is a direct pass to the receiver, and I may have reflections here, right? And I imagine I have only those two paths. And what you can show is that because of these bonds here on the ground, you're going to have interaction between those two paths, and this would lead to received power that will scale in between 1 over r squared and 1 over r to the 4th. Right? So you're going to have something where your received power is proportional to that between this and 1 over r to the 4th. It really depends on how much this one interact with this one. If they interact really destructively, you can show that you have something that may scale at 1 over r4. And so that means there that if you actually, you know, in a very remote areas where you have only two paths and you have one transmitters and you're along a road and you have a good reflections along this road, it may happen that your received power decays much more quickly than just 1 over r squared. You may have a decay in 1 over r to the 4th, right? Because of the interaction between those two paths, and you have only two strong paths here, right? Right. So simplified pass loss model is the following, and this is really what is used you'll use this in the simulation. Very simple. And this was based on actually measurement that people did a long time ago, when people started really looking at mobile communication system design. They were wondering, by taking measurement around big cities, for instance like Manhattan or in New York, or you can take big cities like London, they were wondering, okay, how much can I take measurement of the received power and then do some kind of fitting and try to see how the received power scales with the distance. And so roughly what you can say is the following. You have a transmit power, you have a received power, and you have something that scales as your distance, r, but not to an exponent eta. And so you have your received power scales as 1 over eta. And this eta is between 2 and 8. And that really depends on the environment. So you can have something like a free space and really pure line of sight, you're going to have 1 over r squared. But you can have scenarios where actually, generally speaking, you can go as high as 1 over r to the 8th because of the presence of obstacles also in the environment. And so the pass loss here, so you have two quantity k and r naught. R naught is actually a reference distance so for instance, at 1 kilometers, this quantity k here is actually a constant that is known for this reference distance, right? So you will see this in the model when you play with that. But so that means that you can write the system model, the pass loss, as this quantity in the log domain and you take the -1 in the log domain, actually you take the inverse of this, so you have the path loss is this quantity. So as you increase the distance r, your path loss essentially increase linearly now with n in the log domain. And you have additionally actually a path loss here that comes from your path loss that you have at the reference distance r naught, right? So you will see in the typical model you have k and r naught actually, for instance, given at a certain reference. That's all what you need to do. And then when you drop users in a network, you just calculate the distance, and then you can figure out on average what is the typical received power. Right, so you can do this for higher frequency band as well. It's obviously less mature than the low frequency band, but things have been done in the past few years, right? Because 5G use high frequency bands. Good. So shadowing. So the path loss here is really try to look at the dependency between your receive power and the distance between the transmitter and the receiver, right? The shadowing is try to model a bit more the attenuation coming from obstruction and obstacles, and this is typically modeled using random variable. It's not only deterministic like here, where you have a certain distance, and so that means that you have a distance r, you have a decay that goes like this, right? Typically 1 over r to the eta, and now around a certain distance here, your received power will maybe behave as this, but you're going to have fluctuation around this, and this fluctuation comes from all the obstacles that you have. And one of the effects that we look at, aside the really the short scale fading that we'll talk about, is also the shadowing. And the shadowing is really comes from general obstructions, a general attenuation from obstacles. And this is modeled using random variables, and typically a log normal random variable. And why is it random variable? Is because you have many of those obstructions, and so because of that, you actually can use the the law of probability, like the central limit theorem, and model this, assuming you have many of them. You can model this using some normal random variables. And so what we say here is that the shadowing is typically modeled as a log normal random variable. So that means actually the log of that random variable is normal distributed. You remember this from the probability modules. So S is my random, shadowing. In the log domain, I have S in dB, and S in dB here is normal distributed, right? With a certain variance. And this variance is typically between 4 and 12. You will play with this. You will see it in coursework 3 when you have to evaluate the whole network. So what that means that often, when we look at the log domain, what we take into account is the path loss and the shadowing. So you have the path loss, which is given by the path loss at a certain reference. Sorry. This 0 here, which is the reference plus this quantity here. And additionally to that, you add the shadowing in the log domain as well. So you have here the path loss, and here you have the shadowing. Right, so your receive power is given by your transmit power, your K that we had there in dB, right? And then you have minus the path loss there in dB. So that's going to be your path loss, and that's going to be your shadowing. Now that this is normal distributed with mean equal to 0, so actually what that means is that if I look at here, it means that around this distance here, I will have a shadowing that in dB will be normal distributed like this, right? And centered around this, right, in dB, right? So it can boost up the power or decrease the power, and because it's a statistical variable, this is what happens. So your mean is essentially really your path loss, and around your path loss, you're going to have a random variable that will vary relatively slowly at the second level or the minute level that is log normal distributed. That's what it means. Right? Any questions here? Feel free to interrupt me, right? If you're still there. Right, so where do we use that? Where do we use this path loss and shadowing? So you will look at this in the coursework 3, but one way to look at that is to use that is to have a very quick understanding of the SINR, so the signal to interference plus noise ratio that we have in the network. And so the signal plus interference to interference plus noise ratio essentially is given by the following. This is the energy that I transmit at a certain transmitter I. This is the pass loss or end shadowing that I have, which is my lambda here, right? So it's my lambda in dB here, right? So essentially it characterizes the, if you take it the natural scale, essentially, you're going to have this quantity here. So 1 over, there's a minus because the lambda is essentially proportional to r theta. So the lambda minus 1 will be 1 over r theta. And then additionally, you have the shadowing. We'll have some more expression of this later on. But this is essentially characterized, taking into account only the shadowing and the pass loss of the signal strength, of your desired signal strength. And then you have at the denominator, you have the noise, and you have all the interference that you can have from other transmitters. So for instance, here, let's imagine that my user Q here is this one. This is my user Q. And is in cell I. This is my cell I. So he received a certain signal power on the red arrow here that is proportional to this. So I have a transmit signal power multiply here by my pass loss and shadowing. This is my long-term received power. And then I divide by the noise I experience at the receiver and the sum of all the interference I see from those red lines here. For instance, from this transmitter, and this transmitter will create some interference. The strength of that interference, if I look at just from a long-term perspective, just taking into account pass loss and shadowing, will be given by a sum of those quantities, which is, this is actually the strength of the power I experience from this transmitter, and then for another J, I'm gonna have from the other transmitter. So this is actually something you can look at, and you can draw a CDF of this, so cumulative distribution of function of this. Once you drop many users in a network like this, depending on the distance, you're gonna have a different pass loss. You can have the shadowing will be anyway random, and so you can draw, once you plot, you drop many users, you can compute the SINR for each of those users, and then you can compute the CDF of the SINR. And so a typical CDF, for instance, is as follows. This is your long-term SINR, wideband. Don't think too much about wideband here. It's just long-term in the sense that it does not include the small-scale fading, just includes the pass loss in the shadowing. So this is a typical CDF that you can get. You can focus just on the 2D for the time being. And it says that, well, your SINR, roughly, that you will experience in a cellular network, range between -5 dB and 20 dB with the dashed line. Right, so that's what it says. That is the strength of your SINR in a typical network. 3D here means that you have the antennas at the base stations here. You're able to tilt them so that you focus a bit more on the user. So instead of blasting energy horizontally, you orientate them a little bit more towards the ground, and that helps to reduce the interference to the other cells. And by doing this, you see that your CDF is shifted to the right and evolves between -5 and 20 something dB, right? So this can change, it can move a little bit, but this is something that rough idea is actually quite reasonable values. Right, so obviously, if you're at 20 dB SINR, you can transmit at a much higher rate. You can receive much higher rates. So you would probably, the transmitter will transmit with large constellations, no 16.4 QAM, 128 QAM, or 256 QAM. If you're here at -5 dB, you have very low SINR, so you have very limited rates. So you're going to have maybe BPSK, QPSK that are going to have to be heavily encoded as well, right? Good. So so this is what our narrowband channels looks like now, if I include the small-scale fading and the pass loss and the shadowing. So we had this h of k, and you look at the different notation here. I have a h of k here that was actually, I would say, straight h. And now I'm writing this straight h here as a function of three terms. I have the path loss, I have the shadowing, and I have here the small scale fading that is written in italic, right? So my path loss here is directly proportional to r to the n, to the eta, right? So this is exactly what was written here. And I have a square root here because I'm looking at the channel gain. If I'm looking at the magnitude square of this, which would relate to the received power, then obviously your received power is a direct function of eta. So that means the magnitude will be a function of the square root here of the lambda, sorry. I have the path loss, I have the shadowing. So this is log normal distributed. This is simply deterministic based on the distance. And now I have this last term here, which is the small scale fading. Right. So a different way of writing this is simply writing the following, where now this lambda, the square root of lambda here is actually captured. This lambda is lambda 0 multiplied by s, captures the path loss and the shadow. Now this h here is now the small scale fading. And so the small scale fading is the fact that aside those, I will have many paths, and so those paths will be blocked by obstacles. So that will be actually the modeling of this comes from the shadowing, but there will also be constructive and destructive interference of all those paths at the receiver. And if I move just by half a wavelength, you can imagine that actually all the phase of all those paths will either constructively or destructively interact. So if I just move by half a wavelength, actually these constructive and destructive interference can change quite dramatically, right? And this is what is captured by this small scale fading h here. And so this will be modeled as a random variable. And we're saying that actually the strength of this quantity, so how much it contributes to the power, will be related to hk square, right? And I can take an expectation of this because I'm going to have a random variable. I'm saying that actually this is equal to 1. So that means that on average, this quantity here will not create, will not increase or decrease the power. And so if I take this figure here, it means that I will have shadowing on top of the path loss, but additionally, I will have small scale fading, so fast fluctuation. But the small scale fading on average around that distance r on average will not change the average power, right? The shadowing on average will not change the average power, but it will change the instantaneous power because those are random variables. So obviously the instantaneous realization of those random variables will change. And so what that means is that if I draw this, so for instance, if I only count for the path loss, I'm going to have something like this. If I now take into account path loss plus shadowing, I may have something that may vary like this, for instance, right? And you can have a different realization because the shadowing is a random variable, but imagine you have this. And if I add now the effect of the fading, the small scale fading, which is really fast fluctuation, I may have something that looks like this. This is instantaneous received power, right? So you have a general trend that decays with the distance. You have a general trend that will fluctuate as a function of the shadowing, and then you have your instantaneous final power that will be a function of the large scale of the small scale fading. That will be those fast fluctuations. If you move by just half a wavelength, this constructive and destructive interaction can change completely. Right. Good. So let me have some reminder about some fundamentals of probability, because we're going to use this to model this h of k. And so you will see this in a minute. We're going to use a complex Gaussian random variable to model h, and so that means that the magnitude of hk here will be Rayleigh distributed. And so I just want to remind you these kind of things. So this is something you have seen for MSc students. You have seen this probably in your undergraduate studies. You have taken the probability and stochastic course with my colleague Chongling. So this is not something that should be too surprising to you. For our MN students, this is directly related to what we did in second year probability. Right, so remember what is a real Gaussian random variable. It has a certain mean, a certain variance. This is a classical PDF of a real Gaussian random variable. You have a standard normal random variable when mu is equal to 0 and the variance is equal to 1. Right, this is a standard Gaussian, standard normal. I will not really call them normal here. I mean, the Gaussian will come quite often, but normal and Gaussian is the same thing. Now, when you have, we're going to play with complex quantity. And so what we're going to have is something like this. Now we have a real part and an imaginary part. And if we say complex Gaussian, means actually the real part is Gaussian distributed and the imaginary part is Gaussian distributed. So you can view this as a vector of two random variables where the entry is actually real Gaussians. Right? That's what it's saying. Now, one specific case of Gaussian random variable, which is called circularly symmetric complex Gaussian random variable, is really the case where the real part and the imaginary part are both Gaussian random variable with mean equal to 0 and a certain variance sigma square. But those real part, imaginary part are also independent and identically distributed. So those are two random variables, but are completely independent, identically distributed. The same distribution, Gaussian, same mean, and same variance sigma square. So what that means is that if I look at this from the top, and I have explained this in the second year math, you have essentially like you have the real part and the imaginary part. You can say this is like kind of Gaussian, right? In the real part is Gaussian in the imaginary part. And if you from the top, it looks like a hill, right? The joint PDF looks like a hill that it has perfect symmetry, around 0. That's what it says, because the real part, imaginary part have the same variance. If one of them has a larger variance, then you're going to have kind of a hill that is shifted in some direction. We have perfect symmetry. So this is what is called circularly symmetric complex Gaussian random variable. If you have that, and you take the magnitude of this quantity, right? So you take the magnitude of x, which is essentially the square root of the square of xr plus the square of xi. This is actually really distributed, right? And this is something you have those modules, and we have done in probability second year as well. You obtain that by doing a change of random variables. You have two normal random variables. You can go from two, you can do a kind of change of coordinates. You go from Cartesian coordinate to polar coordinate, and from there you can get the PDF of the magnitude, and you can show the PDF of that magnitude. So this quantity that I call S here is really distributed. Is really distributed as is given by this. And the phase of this will be actually uniformly distributed over 2 pi. Right, one more reminder is the following. So now if you take S, take the square of S, so you have a Rayleigh distribution, Rayleigh distributed random variable. Now you take the square of this. So it comes to saying I have two normal random variables here, complex normal random variable. I take the magnitude square of X. So I end up having the square of a normal random variable plus the square of a normal random variable. The square of a normal random variable, this is a chi-square random variable. We have done this in second year probability. Now you have the sum of two independent random variables here, where you see xr and xi are both normal. So I have the sum of those two. So this is actually called a chi-square with 2 degrees of freedom. I have 2 degrees of freedom because I have the sum of here 2 chi-square essentially. And we can show that actually a chi-square random variable with 2 degrees of freedom is nothing else than an exponential random variable. So you can say that x squared here, so the magnitude square of this complex Gaussian random variable is actually exponentially distributed. And so usually we write this as lambda e minus lambda x, right? So my lambda here is 1 to sigma squared. Right? Now what we were saying before is that you remember So if you have an exponential random variable, if x here is exponentially distributed with parameter lambda, the mean of x is 1 over lambda, right? So 1 over lambda here would be 2 sigma squared. So actually, the expectation of y here is 2 sigma squared. Good. So this is a reminder, and now we're going to use this to model this. So I was saying earlier on that here we have this quantity here. So let's imagine now that I want to model H as a Gaussian random variable, circularly symmetric complex Gaussian random variable. So that means actually the magnitude of H will be Rayleigh distributed. The magnitude square of H will be exponentially distributed with parameter 2 sigma square, right? So the expectation here of this expectation of H square will be 2 sigma square will be equal to 1, right? And I assume it's equal to 1 because on average, this fading does not increase the received power, right? So I'm going to play with actually random variable or exponential random variable or normal random variables, where in the real part and the imaginary part I have essentially a variance that is 1 over 2 here, right? That's what it means. Right, so this is how we're going to model this H. We're going to assume the real part, the imaginary part, are the real Gaussian random variable. In other words, they're circularly symmetric complex Gaussian random variables. And the reason for this comes from the central limit theorem. If you have a lot of different paths, you remember, and you sum a lot of random variables together, and those random variables are ID, you may not know the exact distribution, but if they're ID, the sum will actually look Gaussian distributed. And so this is what we use here. H comes from the contribution of many paths, right? You have many paths that will constructively interact or destructively interact with each other. But because you have many of them, you can, in the limit of an infinite number of them, you can assume this is actually Gaussian distributed. This is where it comes from. So we're going to assume H is circularly symmetric complex Gaussian random variable. So we have one random variable there. We're going to assume S is log normal distributed, and the path loss is simply deterministic. Right? So we have here two random variable, log normal random variable, and a Gaussian random variable that we're going to play with. So in the coursework 3, for instance, you're going to play with the log normal. On all the other coursework, usually we're going to ignore for the time being the effect of shadowing and path loss, because this is always something you can add, but we're going to look at mainly the effect of the small scale fading. So we're going to play quite a bit with this Gaussian normal random variable that transforms into a Rayleigh random variable for the magnitude and the exponential for the magnitude squared. Right, so let me finish with this. So I'm going to have essentially my channel H will be HR plus JHI. So the magnitude of H will be, you can call it this S, and this will be then Rayleigh distributed. The expectation of S squared, so that's actually the second moment of this random variable S, will be normalized to 1. You can find the expectation of S as well. That's the expectation of a Rayleigh random variable is given by this. This is not so important. So the magnitude is Rayleigh distributed. The phase of this H here will be uniformly distributed. And now, why is this important? Is because if you look at the distribution of that, essentially, what you will notice is that you have maybe something that looks like this. So that means that if your H, your small scale fading, is distributed as Rayleigh, you're going to have, as time goes by, you're going to have something that will fluctuate very quickly. And so you may have at a certain time instance where actually you have a quite good channels, like here. Let me change the color, like here, for instance. And then the next time instant, right, you drop into something that is very low. And so you see that you go from 5 dB instantaneous power here, or instantaneous contribution of the fading, to minus 20 dB. And so you lose 25 dB suddenly, because of those constructive and destructive interaction of those multiple paths. And this is obviously a major problem. If you lose 25 dB, you can think about what happens here, right? On average, at a certain distance, you may have, let's say, a user maybe at 10 dB, and then, but it fluctuates around 10 dB, and suddenly you may lose a quite significant amount of power because of the small scale fading. So your instantaneous SNR now suddenly may becomes very low, right? Or it can become instantly much higher also, because suddenly you benefit from this fading, right? But getting very low, it's a problem, because obviously if you transmit at a certain video, suddenly your SNR becomes very, very low. There is no way you can retrieve this. So you need to find ways to actually make the system more reliable. And this is what we're going to look at. Okay, good. So let me stop here. And we're going to continue on Monday with fading and diversity. Right, any questions, feel free to let me know, or you can also contact GTAs. Long Fei, you will have all the information soon on Blackboard. Okay, thank you for your time. Hope you actually enjoyed the first lecture. It's the very beginning, so nothing fancy at this stage. And I see you next week. It's 2 p.m. on Monday. Thank you. Bye-bye.